to talk on education, simply because education was very important part of work of your department, and also I wish to say a few words about my old friend Evgeny Hukhro, because this year is 50th year of his pedagogical work, of his work in teaching. Exactly half century. It is already quite impressive on its own. He started to do that in 1974. He was in the first year at Novosibirsk University, and he started to do in mathematics correspondence school, mathematics school by correspondence. It was quite an interesting establishment, about 1,000 students, stretched over 7 time zones, of quite advanced level. To teach there required actually some skills, some experience, and very good understanding of at least elementary mathematics. It so happened that for some reason, which I have no time to discuss, the school was in crisis, and Evgeny was invited, and some other of our friends to help, basically. I also was involved in that, but it was Evgeny who was really instrumental in rearranging everything in the school, and eventually became its director. I believe at the time when he was kind of a postdoc, if I'm not mistaken. And also, practically at the same time, in the second year at the university, he produced his first paper. And also, from the very beginning, got involved in preparation and running of mathematics competition for school children. He did everything at once. He was involved in all aspects of academic work, in effect. And he became, as it was expected, a professional research mathematician of quite serious achievements. But he was always teaching. So he came to Lincoln with colossal experience. Well, Andrei already said about that today. I had a chance to see him teaching in many very different situations. And what was interesting, 2 aspects I would emphasize: precision and attention to basic, to fundamentals. He never moved ahead without securing backgrounds. He is one of the few lecturers who I know who, in teaching linear algebra, in the very beginning, you know, when the systems of linear equations and then elementary row operation on matrices, he was one of the few people who I knew who wished to spend a few minutes explaining to students that these manipulations with matrix, extended matrix of the equation, system of equation, are exactly those which preserve the set of solutions, transform a system of equation to an equivalent system. And actually that the final answer, that x equals something, y equals something, z equals something, is also actually a system of linear equations, but equivalent to the previous one and written in a transparent and usable form. Well, a few words about teaching algebra in Lincoln. I heard today from Andrei that it was Evgeny who founded the algebra group. I had a chance to see actually how teaching was going on. For the last 4 years, I was external examiner of pure mathematics in Lincoln. And I can say with confidence that Algebra Group set from the beginning and maintained excellent standards and very nice style of teaching, which is also important. Well, what was the style of teaching? It was student-centered. Focus of work was on students developing, achieving understanding of material. Understanding what as everything. Excellent didactic transformation of material. Quite a challenging stuff was presented in a form accessible to students. You know, before being external at Lincoln, I was external moderating examiner of Part 1A at Cambridge. And before that, very interesting university, Glasgow University, to Scotland, different organization of everything. For example, their degree is 5 years of university study. And I said excellent example. Lincoln was definitely in the same league. Very different university, very different students. But it was a pleasure to read exam papers and frequently exam scripts as well. Before I started to act here as an external examiner, I once had a horrible experience at my own university when because of some reason, I was asked to mark exam course, basic course in algebra style, actually, in year 1, taught by one of my colleagues. And examination was set by my colleagues. Marking exam brought me to physical illness. It was intolerable. It was something like what, systematically kills kittens or something other cute creatures. Lincoln, was very difficult. It is a breath of fresh air. I will take the lead from Evgeny's lecture in 2018 under the title "Is Algebra a Spoil Sport in Mathematics?" In that lecture, he was proving that algebra could be interesting, it could help in life, it could solve this and that, but it was a lecture for general audience, basically. I wish to be more focused on purely professional issues and discuss how it is possible to make algebra less boring for students. And we'll consider 2 large examples today, which came from my experience of teaching, and also they came from opportunity which I had for many years. How many years it was? 19 minus 6, for 13 years every summer. I had a chance to teach an experimental course at a quite interesting establishment, Nesin Mathematics Village in Turkey. There are some systemic issues which still affect university level algebra and which are not properly addressed in textbooks, for example. And I will mention two of them, hopefully, time permitting. Yes, this is a picture of Nesin Mathematics Village. Quite remarkable place in Turkey. It is 2016 now, actually. it looks much, much, much more beautiful. My first theme is abstraction and generalization. How to develop ability for abstract thinking in students. It is a very serious issue, and at my university in Manchester, it was a sad situation then. Perhaps half of our students were reaching their end of third year, being unable to understand why equivalence relation defines a partition in classes of equivalence. Too abstract. Well, I was experimenting with that in the Nissan village. My class, for example, on different topics, specifically on abstraction, was about 20 fresh school leavers who finished school, passed exams. Now, on the basis of these exams, were admitted to universities. But it was summer studies of universities, lectures were starting in autumn. So they decided to come to mathematical village and take intensive courses in various topics. One of these courses was mine. It is 1 week, 10 or 11 hours of lectures over 5 or 6 days. Topic: a parallel development of divisibility theory for integers and for polynomials. Well, how it was taught? There were two blackboards in the garden next to each other. One board was used for definitions and statements and was divided into two halves by vertical line. On one half for all that stuff for integers, another on polynomials. Second board was reserved for proofs and examples. Every definition was given in two versions, for integers and for polynomials, and I wrote them on the board. Very soon, I was given a definition for one side, chosen at random, and asked students to describe the corresponding definition for another. Students loved this game. Lemmas and theorems also were formulated in two versions for integers and polynomials, and I asked students which one to prove. The other was given them as an exercise. Of course, everything started with division with a reminder. And also some standard results about integers, say the Fermat-Little theorem, and polynomials were also proved in the way. Well, nothing really special. What was interesting, that the course was the apex of the course was Lagrange's interpolation formula and the Chinese remainder theorem for polynomials and for integers. It was becoming clear that this is one and the same theorem. Fact which normally never mentioned in mathematics department of university. Various definitions from algebra, rings, fields, domains, say, were introduced when it was becoming appropriate to introduce. As a result, when we had Lagrange's interpolation formula and the Chinese remainder theorem, it was possible to develop in a dialogue with students the concept of Euclidean domain. and prove these theorems for them. Well, the one theorem actually. And then actually to prove that Gaussian integers, these are complex numbers with integer terms, a plus bi, where a and b are integers. The Gaussian integers form an Euclidean domain. It is quite interesting proof, by the way, which explains quite a lot about complex numbers. And after that, the very last lecture was a proof of Fermat's last theorem for polynomials, not for integers, or for polynomials over complex numbers. And what was used there? That Gaussian integers, which were obtained by adding to integers square root of -1, or all four roots of quartic equation, x to 4 equals 1. That a proof of Fermat theorem for polynomials required adding two coefficients, two coefficients of the polynomials involved. Possibility that they belong to the extension of integers by roots of unity, so-called cyclotomic algebraic numbers. And this new ring is does not necessarily have uniqueness of factorization into primes, as it should be in Euclidean domains. But it works for polynomials. For integers, it would not work, because there are cyclotomic extensions of rational numbers, where for in algebraic numbers, cyclotomic numbers, there is no uniqueness factorization. And this perhaps was a mistake by Fermat. Well, basically, it was developed all this stuff basically for school children. They have not spent a day at the university at that point. It was great fun. And what important, everything, almost everything, of course, with the exception of example, quite difficult, of non-factorization, of not uniqueness factorization, some specific stuff. Absolutely everything was proved. Short, beautiful proofs, sequence of them. And there's a lot of problems for students and exercises. One example at random. Find the remainder upon division of polynomial x to 2023. Oh, sorry. At that year it was 2017, I got upon x squared minus 4 is becoming an accessible exercise. And most likely students were involved. I try to suggest at some point, before COVID, there was some review of our courses, and I suggested this kind of introduction to mathematical thinking and to proving stuff in the first semester of first year for fresh students who just came. Alas, it for different reasons it wasn't accepted, which I very much regret. So this was my one example. Another one is about duality in linear algebra. This is a bit more serious. Well, it is well known. So when we buy some goods, my example was apples, bananas, and oranges at certain prices, in certain quantities. The total price paid is this expression. Basically, linear algebra starts with manipulation, as manipulation with expressions like that. It can be conveniently written as a product of a row vector and a column vector. And which explains the way why multiplication of matrices follows this rule, which is never explained to students, why we multiply rows by columns. The rule of transposition appears from the very beginning. So all this very nice and good, with the exceptions that apples, bananas, and oranges, and vectors made of them, and vectors made of pounds of sterling or dollars, or whichever, cannot be added. They live in completely different vector spaces. Moreover, this fallacy starts in school mechanics. Work cannot be the dot product of force and displacement, because force and displacement live in different vector spaces. They cannot be added. Vector spaces are different. Physicists are more accurate. Andrei could correct me, perhaps. They write a very interesting expression. They move indices in different positions. For rows, indices go in subscript. For columns, in superscript. And moreover, they omit the summation side. Remarkably, this particular trick was invented by Albert Einstein when he started to seriously work with the tensor notation for geometry of manifolds, differentiable manifolds, in the general relativity theory. The solution for that is moving to set up when the principal object of algebra is the pair of a vector space, finite dimensional vector space, and its dual. Its dual is a space of linear functionals on space V. And I demonstrated to my students, explained in my lectures, for example, at Manchester, that linear functional is the principal linear algebra concept for algebra. Because when we talk about, for example, how temperature changes over the day, we have the space of all possible functions which represent temperature. It is a vector space. It is infinite dimensional. But taking measurement of temperature at a particular moment of time, it is a linear functional. Linear functional, it is a mathematical abstraction of measurement. What happens? The space of row vectors and column vectors are dual to each other if they have the same size. Transposition is an isomorphism between them. Well, For infinite dimensional vectors, dual spaces quite frequently much, much bigger in size than the original space. Here, various effects, a difference between finite dimensional spaces and infinite dimensional spaces start, which need to be explained to students. In Manchester, I always gave them example of a basic space of sequences and linear transformation on them, which has left inverse but does not have a right inverse. In finite dimension, if a transformation has a left inverse, it has a right inverse as well, and vice versa. In this setup, we have a quite different view on many other things. For example, linear form on the space V is a homomorphism from V to its dual. Inverse matrix, if we see it as a basis in V, matrix, rows of invertible matrix, of non-degenerate matrix, form a basis of the space V, say. Then the inverse matrix is the basis in the dual space, which is equivalent, which is dual to this original basis in V, and a lot of other things. And remarkably, all that is simplification, provides serious simplification. With one more thing, matrices have to be written in more natural form. Indices for rows and for columns have to be in different positions. One interesting thing that once in my previous life, I once taught a course of linear algebra in this conceptual framework, with clear in tensor notation, basically. It was a lecture course of linear algebra for students in physics. The syllabus, for some reason, demanded develop linear algebra, analytic geometry, and some tensor analysis. In one lecture in the second semester, in one lecture course in the second semester of year one. I understood that give to tensors to second year students, to first year students, is it is something impossible. And so for the reason, from the very beginning, started to work in tensor notation. It worked remarkably. For me, it was a pleasant discovery. I would continue to teach linear algebra the same way. But unfortunately, in the standard courses in linear algebra in universities, the use of tensor notation, first of all, there are no textbooks, not a single textbook. Unfortunately, what a fossilized already tradition of sticking to some particular notation prevents many serious changes in teaching linear algebra which are needed. Where traditional matrices come, and why they were not presented in this form from the very beginning? Well, it can be explained. Definition of a matrix in the paper of Cayley of 1858. look at the typography. I will try to increase the size of the screen. No. Typesetters had to use what they had. There was simply no technical means to use both upper and lower indices in the same thing and arrange them after that into some kind of a table. Now we have a fantastic typography provided to us by Tech and LaTeX, but it is too late to change anything in that approach to teaching. This is the issue. What basically all that I wish to say a bit more in various places of my talk today, but I was lost time because of all the trouble with my connection and everything. And so for that reason, I have to finish at this point.